Okay, so I think we already introduced some session. They will include the preliminary knowledge for the idea. How can we describe anything in the space? Okay, so next, I think the most important part is that we need to introduce the coordinates. So in today's class, in the very end, I will teach you how to use the MATLAB to do the matrix transformation. Actually, in the exam, it's welcome you to bring your code because you already have some practice. And if you want to solve any kind of coordinator transformation problem, then it will be easier that you just use your code. Okay, so if you do your homework good, well, and devoted, then you'll be fine in the exam. Okay, so the beginning of this today, I will start to introduce if there is an object in space, then we have a defined coordinates. We want to rotate with it. Actually, we do it all the time. Then how can we do that? But we have a lot of reference frame. So it means we will rotate several times. So there are two types of questions. The first two kinds of questions. The first kind will be the robot itself. You just observe from one coordinate and then do the motion. So the motion including the movement and the rotation. And the other the other kind will be you observe from different coordinates to the robot. Okay. So I think the best way is to visualize because I know everyone already used to visualize everything. The wording sometimes is not helpful. But over here, I just highlight for you. In a PowerPoint, yeah, we just teach the English presentation. We don't want to use too many colors, but the different color can reflect the important session in this slide. So for example, I will introduce the rotate with the current frame. And also the second kind is called rotate with the fixed frame. And how can we combine it together to do the motion description or position description, something like that. Okay. What did I mean? The rotate with the current frame. Yeah, as I mentioned, use the visual. It will be easier. So as you can see from the top right side, there is a coordinate. So just focus on the solid line. The solid line coordinate is the original line. And the dot line represent the coordinate already be rotated. For the first one, what kind of coordinate it rotated with? Which coordinate it rotated with? What did I mean? 它绕着哪一个轴转? For the first one, well, first one is the left side, is y. Correct. Okay. It rotated with y, and it has a new coordinate, which is the middle one. The middle one already rotated with y, so they have a new z-axis. They call z2. Okay. At this point, it rotated with z, rotated with the angle called theta again. Then they equal to the final one. The final one is the dot line represented the coordinate. It's called x2, y2, z2. Okay? Let me compare the different for fixed frame. Oh, I don't have a fixed frame. It's weird. Okay, because it's too difficult to draw. Okay. It makes sense a lot because in our human being, we like to do something after. So we make a mistake and we tell more lie. to make up the mistake. In this point, it's very similar. Yeah, we already rotated to somewhere. Then we continue to rotate. But there's an issue. I want to indicate the issue immediately. Then we go to the mathematical part. What is the issue for that? Can you imagine that? If I just rotate, yes, it's very straightforward. I rotate the coordinate. Then I rotate the new one. And then I rotate the other new one. It's very straightforward. But what is the issue? You may think about what kind of issue. Yeah, if you read through the whole textbook, not whole textbook, just this chapter, you will know. Anyone? Anyone want to try? What kind of issue it may cause in this kind of rotation? 有人要试试看吗？等一下跟我报名字哈。Anyone? You want to give up this opportunity for your score? You want to try? It's straightforward, it's good, but sometimes it's straightforward cause some issue. That's the reason I think we have a mathematician exist in the world. Okay. Okay? No response? Okay. The issue will be in the next page. It will be confused because I just mentioned we rotate the y-axis first, right? Then we rotate the z-axis. Then we have the final rotation matrix. Perfect. But if we did not follow the sequence, 顺序, we rotate the z first, then we rotate the y. Then you definitely will not gain the same rotation matrix finally. So this is the proof. It means if you rotate with different sequence, did not follow the sequence, then by this way, you cannot have the same rotation matrix. Although you rotate y and z also, but the sequence is better. So this is the issue. Okay, so I jump to the conclusion, or then let you get a picture, say, oh, okay, there's an issue, but what is the issue caused to us? Later on, we will introduce to you. Okay, so for the straightforward part, there will be the reason. Today I will teach you a little bit. If you know the MATLAB, it's good because MATLAB is a very good tool to compute the matrix operation. Okay, so over here, when I rotate with the y-axis with y, and then I rotate with the z-axis with theta. So the matrix, rotation matrix we just introduced last week, then we can multiply together. Then the final matrix is messy. Okay, later on will become more messy, so you need a tool. Okay, so this is the final result for, they call R. Okay, remember the format this time. It's okay, I can go forward and backward. Okay, then if I rotate with different sequence, I rotate with Z first, then I rotate with Y, same angle, the same angle. But you compare the matrix 2.18 and 2.19 will become different. Okay, still works. Yeah, if you follow the rule. So let's maybe that's a later story, but I can tell you first. So when you design or not design, you produce a robot and sell to someone. Then someone always asks about what is the coordinate it derived from? What kind of system you derive for your robotics? It's quite important because they need you to provide the relative information for that. Then they can do the later on maybe research or application. Yeah, okay. So over here I have a concept. Okay, so these two slides introduce this part, and for a very complicated one, of course over here because we use the they call symbolic operation. So later on in MATLAB, you can see the very, I would say, elegant format for the symbolic representation. Okay. Any question from here? So these two matrices will be different if you don't use the same sequence. Okay. Done. Okay. Good. So to solve this issue, I guess we need to rotate with fixed frame. Maybe can fix the issue for the sequence issue. Okay, so we kind of derive the full content for the fixed frame. Okay, so many times it is designed to perform a sequence of rotation about a fixed coordinate rather than successive current coordinates. Okay, it will be more not straightforward to human, but for the mathematics calculation is more straightforward. Okay, so they want to rotate it with a fixed frame. Jump to the coordinate. Okay, I don't have a coordinate. It's weird. Okay, somewhere. Okay. In that case, I use the same diagram to describe a little bit. If I want to rotate it with a fixed frame, so when I rotate it with y, I have a new z1, right? But I want to rotate it with z0. So how can we do? Then we need to reverse back to the original coordinate, then rotate it with z-axis, then come back the later on axis already rotated with y. This is a long description, so let's see from the formula. Okay. First, we introduce the simple operation they call R20. What do you mean by R20? Over here, we skip about XYZ. We just mentioned about rotation matrix. We have a rotation matrix R0, R1, R2. And in this representation is I want to observe from the frame 2 to 0. So I rotate my coordinate from 0, middle maybe 1, then 2. This is the combination final rotation matrix. So it includes the R10. I rotate from frame 0 to 1. Okay. Then I rotate from 1 to 2. Okay. So when I combine these two together, then I have the final rotation matrix R20 over here. So it's easy to do the computation because when we do the operation for matrix, okay, the uppercase and the lowercase is the same. Then we can multiply together. Then the final one will become 20. So it makes sense if you observe, you have the concept from the matrix. Okay. So it mentioned what did I say over here? I just previously. I'm saying, okay, so if you want to fix with the fixed frame, then when you rotate it with y, okay, and then I want to rotate it with z, original z. Then I rotate it back, rotate the z, and come back to the whatever I already rotated. Then we can observe together, but already rotated with y and z, but with the original one. Very complicated description, but when you see this one, will become more complicated. So you need to take patience to see what's going on over here. As I mentioned, I want to rotate from 2 to 0. So the middle one, I have a 2 rotation. The middle one is 1, 0. Okay? So I already rotated 1, 0. That's okay for now. But when I want to rotate again to the frame 2, then I need to reverse back. What is a reverse back? I need to rotate it back and rotate whatever I want, which is R. I addressed over here R without upper and lower case script. Why? Because this is whatever you want to rotate. I leave it in empty. Then you can rotate whatever axis you need. So I'm saying over here, depending on the next rotation axis, whatever you want to rotate, you put over here, they call R. But the most important is when you rotate with the first one, then you need to rotate back. Then rotate the new one, then you need to rotate back again. Then it becomes the final one. It's so complicated, right? But think about this a little bit, because this is quite important for understand what's going on. Any question? So this R I leave as I would say empty because it can rotate whatever you like. In our case, maybe in the previous case, we rotated with Y, which is this one. We have the new Y. But we need to rotate back to the original Y, X, Z. Then we rotate the Z again. Then we rotate it back. Then we have the new coordinates with rotate with the original Y and the original Z. It's very difficult to describe, but the math is easy, I would say. The math is easy, especially if you see later on, I will use an example to demonstrate how can we do the operation arrangement, then you will understand. But over here, keep in mind, stay focused, and you will know what's going on. Digest a little bit and see if you can find out any issue. At this point, you already know what's going on, what I'm saying. Raise your hand. Do you know? Okay, I know what's going on over here. You don't know what's going on over here. Raise your hand. Okay. So the rotating with the existing current axis for the first one is easy, logical, right? This one should be okay, right? Should be okay? Okay. Because you rotate already, then you rotate with the new one. Okay. The issue I just mentioned, if the sequence is different, then the final matrix is different. It's not good. For the fixed frame, imagine this. If I want to move this computer to the other laboratory, so I need to move the screen and to the other laboratory. Then I come back to move the other like a mainframe or keyboard again back to the laboratory. It is not good example. Okay, it's not good example. Okay. Rotation is kind of interesting. You know, there's only one thing they will not change for the rotation matrix. Why is that? The origin. Okay, the origin will not change, or because the origin changed, then it means the coordinates can fly to itself. It will not fly to the global coordinate. It is flying. Okay. So at this point, if we want to rotate it with the original one, we like the original one very much. So we rotate it with Y first, but when we want to rotate it with Z, we need to go back to rotate it again and come back to the original one. Not the later one, not later one. Not, okay, it's a kind of lousy speaking. 旋转在固定的轴向，这是什么？哦， 这是课文啊，你要拍这个。旋转在固定的轴向，你必须把它转回去才能旋转。这个好简单啊，我们都是这样转的啊，但是这样转有很多问题啊。我们刚刚讲了哈，那我们今天如果要转的是固定轴，什么叫固定轴？原来那个轴我特别喜欢，那这时候呢，你转完的要把它转回去，再转一次，再转回来。转完你固定轴转的，再转回来。这个可以确保一件事，它确保的就是刚刚讲的那个缺点，它可以确保说，不论你转的顺序如何，它是都 OK 的，它是都 OK 的。当然我们是写在里面啊，我只告诉你说我是绕固定轴转，然后我就给你西塔、阿尔法、贝塔，你去转，但是我没有跟你说先转哪一个。如果你用固定轴的一个式子转出来，matrices会一样。如果你用的是这个 current axis 转出来，顺序不告诉你，转出来就不一样。这就是它的点。OK， 可以吗？好 ，OK。Maybe we should take a look at the example. Okay, so here is the explanation for that. This is a simple one, explanation because it is a general form. Okay, R is whatever you like. Okay, you can turn whatever you need. Okay. So let's go back to the one. Okay, let's still rotate with Y, and Z with theta, but in fixed frame. In this case, we already rotated Y axis with Y and Y. Okay, Y and Y angle. For the first one, I should have a point. This is the first axis I rotate. Did it rotate with a fixed frame? Fixed axis. Original one, I already addressed 3 times. Yes, I rotated with the original axis. I rotated with the original one. Okay, so the next angle I want to rotate with is a Z. The axis with Z, but I want to rotate with the original one. I don't want to rotate with the one already rotated with y-axis. Okay, we can use the simple coordinate over here. I don't want to rotate with z1. If I rotate with z1, let's rotate with current 现在的 axis. No, I want to rotate with z0. So maybe over here, I can address yes, that's what we want. So in this case, what can we do? We rotate back to the along with the y-axis with a negative y. Then we rotate with the fixed frame z, the original z, with the theta. Then we rotate it back again. Then this is the final answer. So the result come out here is R Z theta, rotation Z theta, and rotation Y Y. Compare the previous. Oh, not here. Y, Z. There is an amazing discovery. Compared to the current frame, the only difference is the sequence for the rotation multiplication. the sequence. Then we can achieve the fixed frame rotation. So over here, the process for explanation is a little bit difficult, but the result is so simple. If I rotate it with the current frame, well, it's very straightforward. Rotate the Y first, rotate the Z first, done. But if I want to rotate it with a fixed frame, we inverse the sequence back to the sequence. Then we can obtain the rotate with a fixed frame. So result is easy. Got it? Okay, so this already be proved. If you rotate it with fixed, you just reverse the sequence. Then we'll be fine. Okay, so the big achievement right now, we already done before 10 o'clock is what we finished the introduction to the fixed frame and current frame rotation. Okay, got it? So there are some description in the textbook. For example, the similarity, transformation, it put it in the front. I think it's kind of annoying, yeah, because it's when you did not use that, then you will feel it's nothing. So better you skip the reading and then go to the part is more important. But how did you know where is the important part? I can let you know. Okay. Summary. Okay. So later on, right now I'm so excited, so I need to deliver the lecture. So you need to understand what is the difference between rotating with the current and the fixed frame. Then you can adapt the MATLAB later on, have some idea. For the exam, I will put exactly the same question. So you need to draw for me and explain to me. Okay. If you rotate so many angles for a frame, then will become more complicated, not just 1, 2. So the composition of rotation is you can have a infinity rotation matrix motion activation. You can have a lot as long as you need. Okay, so it means you can also do the composition for the rotation later on. So for the robot, it is always pave the fundamental knowledge for the robot system. Later on we will discuss, because we at least have a 6 frame, need to multiply together. So it's quite complicated. So you need to know, the first one, 2 rotation matrices multiply together. Can we multiply by 3, 4, 6? Of course. So it's called composition of the rotation. And okay, I just accumulate something over here to let you understand more. So for a fixed frame, if I want to rotate the 2 to 0, then we have a 1, 0. And the R is whatever you need. And of course, over here or over there, you should put something, because it is not meet the operation rule. So they did not put 2, 1 over there. But over here, for a fixed frame. But for a current frame, it's easier. So we use the a straightforward part, rotate whatever you need from the sequence you need. Okay, so that's the quite straightforward part. Rotation matrix in space will always be 3 by 3 without the translation. Later on, we will introduce in the end of chapter 2, there is they call full transformation. They include rotation matrix and the translation matrix together. Okay, they have some characteristic over here. So you can, later on, you will use the spatial, I would say characteristic 是特征我不太确定另外一个字怎么讲 characteristic 而已 anyway, okay. So they have this kind of spatial relationship, okay. So when the Rij square equal to 1, then you can do the calculation when you multiply together. And if the I is not equal to j, then we will have the special term. They add it together will become 0, but it's not important. The very important session we will introduce is the 3 independent quantities. The first one will be Euler. So if your robot derived by Euler system, let us know. Or you cannot deliver to the customer. We need to know. Or the Roll-Pitch representation, or the axis angle representation. I would say that Euler and the Roll-Pitch is the very fundamental one you should mention. Okay, you should understand. Okay. So we already built up the concept for the current rotating axis or the fixed rotating axis. For the Euler, what kind of system it belongs to? For the Euler, what kind of system it belongs to? Is it rotated with the current frame or the fixed frame? The Euler is a spatial form. It's rotated with z, y, z. It means it rotated with y-axis, z-axis, y-axis, and the z-axis. Then they can combine the whole system. So if your system is they call Euler system, okay, then they will ask for about this kind of angle for each axis you rotate. You can rotate it with 0. They will be fine, because without the rotate is one of the rotation condition. So rotated with a z, y, and rotated with a y theta, and then rotated with a z, I believe it's called eta, something like that. So it's a grease. I always use this one. Piece, okay, PSI. So with this rotation matrix, okay, where can we obtain the rotation y z-axis? We already introduced in the beginning of the chapter 2. If you rotate it along with the z-axis, the form is the same, only the degree is different, right? And if you rotate it with the y-axis, they will become different. So the final result is what we want. Yeah, with some special purpose, we need this kind of system to describe the maybe the whole situation. Then we can say, okay, I apply the Euler system to achieve whatever I want. Then this is the final result for the Euler system. I need to compare with the other one, then you may know what's going on over here. Let me go quickly to somewhere. Oh, okay. I did not mention that. Okay. This is another Roll-Pitch. Okay. So let me go through the part. I think I'm too lazy to demonstrate all the stuff. Okay. Okay. So this is the Euler system. There's another need. We need to do the inverse calculation, because if we have the angle, it will be fine. But if the user, the needs just provide you the R matrix, they have already have the element quantity on that. Then how can you refer back to the 3 angles? Okay, let me rephrase again. Why I need to know this is a Euler system? Because in some case, we provide you the rotation matrix with quantity, 有数字的9个. We provide you the numerical final result. Then how can you know each of the angle from the matrix? This is called inverse question. It means I already have the result. I need to find out what is the angle for that. And this textbook is great. It just provide you the solution, one of the solution over there. For example, we have a theta angle, right? So he tells you just use the R33. What is R33? It's the location in the matrix. Where is R33? Yeah, okay, C theta. And you can come out with R33, you can come out the theta already. A tangent 2 is a function in MATLAB, but it's an inverse from this book. I already checked. So in this case, in our MATLAB, we need to reverse these two inverse. Then you can find exactly the same answer for that. Arctangent 2 is we have the length number. Then we can inverse the tangent. Okay, so we'll be fine. And possibly you have a 2 answer. Yeah, we did not mention that. Later on we will mention that. Because in, I think we skip the part. The 2 link arm. For example, there's a 2 link arm. We just mentioned, it is not good, okay. We have a final position over here. However, we may have 2 different answers. This is the same type of the robot. We have the same end effect. This is the fixed point. This is the end effect. The same effect will have maybe have a multiple solution. At least for this type, they have 2 solutions. So it's possible the theta have possibly the second answer, which is we list over here. Okay, so you just follow the formula, will be fine. Then you can come out the theta. All he described over here is how can we obtain the number over there. Of course, they have some kind of condition. For example, the sin theta cannot be 0. If the sin theta is 0, then game's over. Then they have a condition. Then both the R31 and R32 are not 0, something like that. They have some condition. If the condition meets, they cannot be solved. Okay. So I will let you do the practice is today, except the multiply the different matrices together. Then we will have a result. You give the number, you give the degree, and you compute the inverse degree to compare with your own to see if it is matched or not. Then this is called inverse process. Inverse process. Got it? Question? Okay. Good. So I say case 1. Here's this function. The function has some special part. I think I just want to let you know over here. Yeah, this is not too much important. Yeah, as long as if you do the computation and if your answer is infinity, INF in MATLAB, then it means it bounces to 0 in your fraction section. Okay, and the theta and y, they all have a formula.是我按到，我以为跳电呢。Okay, so they have a formula over here. Okay, so you can do the calculation. I would suggest you use every time's homework to code your own program, because later on in the exam you can use it. If you use other people's, then you don't know what's going on. Okay, you just copy and paste and get it to me. Let's use this. We have everything in the textbook. You don't need to take picture. Yeah, we have everything in the textbook. Okay, I'm not sure how can you take picture and read at home. You read through your cell phone. Translate what? Translated to Chinese. Then my exam is English. Then you need to translate to Chinese. Wow. Okay. It's a lousy. Now learn from now, no matter how. Because around when I in your age, my English is not good at all. But time will know, will reflect what is your effort. I would say. So try to learn right now, not learn now. Okay, will be easier. And try to read through the whole textbook. Of course, if it's something you cannot understand, just skip. But I would say read the textbook will help. Okay. And over here, I don't want to go to more detail. There are so many extra conditions. Or for example, if the R13, R23 equal to 0, then there's something different about this. Then yeah, you can see some special term over here. Yeah, you already addressed in textbook also, but I don't want to go to the detail part. Okay, and before infinity. Okay, yeah. So will be more safe is if you input the angle by yourself. You don't input a 0. Yeah, you don't try to find your trouble by yourself. Then you can earn some concept that what is the inverse calculation. Okay. For the Royal-Pitch, I think it's worth to describe, but let me take a look. After we finish the rotation session introduction, yeah, we have a Euler and Royal-Pitch. Royal-Pitch, I think I just delivered it as a homework to you last year. Okay, but it makes sense. It's okay. Okay, so the rigid motion is not only the rotation. So we need to combine with the translation together. That's why I need to go through this part very quickly. Not quickly. We need to finish the part. And I can tell you exactly the exam question I will show you in the exam. I will ask you to do the translation for this part. Don't care about this one. This is a robot, something like that. But they have a fundamental global coordinator. They call global coordinator. So there are so many coordinator on that. Coordinator frame 0, frame 1, frame 2, and frame 3. That is exactly the question you will face in the industry. Because you need to use the CCD to guide your robot to somewhere to do something, right? So how can you how can you convert the vision coordinator to robotic coordinate? That's what we need to do in rotation matrix. So it doesn't matter, you already have the robot maybe purchased from the company, and you have the CCD system purchased somewhere in eBay. Not eBay, we don't have eBay. Shopee. And but how did you know their coordinates for the working space? Okay, this is the question I will ask you. And all the stuff we need to use, all the mathematics we need to use, is the transformation we have learned. Okay, so we need to convert for the rotation station. This is the global coordinate. So we need to convert the coordinate, align the coordinate together. For example, this is a y-axis. That will be fine. This is a y-axis. That will be fine too. However, the CCD is upside down. It's on the top. And it can look down to the working space. So how can it define the position from the CCD, then transfer back to the robot? So this is the all transformation matrix. Okay, so we need to come out the idea or say, oh, how can we do that? And this is the accumulated knowledge we have delivered in these 2 weeks. Okay, so over here, we already finished the rotation matrix so far, okay? And how can we combine with the translation? Because this is only pure rotation. Where is the translation? We need to know, okay? And over here, we introduce one very elegant, I would say elegant, but later on there is a DH form is more elegant. But we will have a very well transformation matrix called homogeneous transformation. Okay, they can do whatever calculation for you. So if you have this tool at hand, it will be easier. The idea is we have learned everything, but we need to combine together. We have a position, but the position, if there is located in somewhere, and it did not align with the other coordinate. For example, I need a z in this position, but there z is in the other position. Then we need to rotate somewhere z to align with my z-axis, something like that. So you need a one rotation matrix for your position. We need a one rotation matrix for your position. So we described this in our, I think last week. Yeah, we have some position calculation, even though our answer is not completely correctly, but the meaning is same. We need to transfer some skew, rotated, not aligned frames to our aligned global coordinate. So, for example, over here there is a position vector called P0. That's not important, but we have a P1. It seems P1 sit on the frame 1, no matter where is the frame 1. I need to rotate it back, or I need to refer it back. Referred is more accurate word. Referred, 参考回去 frame 0. So the rotation 1, 0 is the rotation matrix between the rotation frame 1 and 0. Then they can convert, okay, they can, yeah, I would say convert the position 1 back to the frame 0. Then every coordinate on the coordinate 0, then you can do the operation for addition. So you can add it together. Then you have the final position for that. So the fundamental concept is the same. Then how can you dealing with that will be a little bit need some tool. I would say need some tool. Okay, here is you can have a very complicated one. But I want to introduce over here is how can you do the transformation. Okay, let me go to the quicker part and then you will not lose your patience. Okay, so when you do the translation X, then you will align the rotation matrix to 1, 1, 1, 1, 1, 1. But you put your x-axis or x-coordinates over there. Then you finish the one, the translation matrix for x-axis. The same with the y-axis, z-axis. So this is a transformation. So you can see we expand the original rotation matrix 3 by 3 to 4 by 4. Then we can include everything. Later on, the DH form exactly use the same form, but they can be more condensed. Okay, so here is the XYZ for the position, and here is a similar to our rotation matrix, just have the expand transformation. So rotation Z, Y, X. So you have a 6 rotation matrix. So no matter where it is, you can do the computation back to whatever you want. At least we have a tool to do that. Okay? So before several page, I already skipped. It's the same concept. They just describe this one. For example, if you have an H, what is H? H is a weird matrix. H, although is 4 by 4, but for the original R, for the capital R, is 3 by 3. So if you can realize this one, then you are on a successful way, I would say. Yeah, because you already know, oh, okay, this is just the presentation for the matrix, and I know this is a rotation matrix, and the D is for the translation matrix. So original 3 by 3 we discussed for a while. For the last week, we discussed about the position and how can we rotate the position from frame 1 to frame 0, something like that. Then eventually they can summarize into six elegant matrices to do the transformation. For this one, it's called basic homogeneous transformation. It is not necessary for robot. It can use it on the robot system, yes, but it is not necessary only for robot. It can for everything. You need to convert the coordinate in space to somewhere, okay? And the previous page just explain where did it come from and what's going on for that, okay? I want to introduce this one a little bit. They give it a special name for NSAD. You just see over there. I would say it's quite annoying. Yeah, but later on, if you are in the robotics field, you need to be very familiar with this part. Okay. For example, for the first 3 by 3 NSA is all rotation parameters. So when you move to somewhere, for example, if you have an effector on robot and you move to somewhere, this is somewhere we have a position. So we have a dx, dy, dz, they will be fine. But what is the orientation? What does the orientation means? It means you need to pull up your finger. If the finger point to somewhere, they will have a different NSA matrix. So you have a different NSA value for the part. Then you need to do the inverse kinematics to compute what is the angle, rotation angle on our robotics. Okay? So it's quite different. Yeah, how can you compute the orientation in space? Okay, so you need to have this information. But for the position, it's easy. Yeah, just X, Y, Z with like the hand like a Doraemon. But if you have finger, everything becomes different. So orientation is the information they need to provide. In the future, you need to provide, then do the inverse calculation. And the more detailed part, I will leave it to somewhere. Okay. Over here is the same, but we just practice again. If we rotate with x-axis with alpha, the first one, and the current one. Okay, so if the current one, we just multiply 1 by 1 to the right. But if you need to multiply by fixed axis, you need to multiply to the left. Okay, that's a simple one. Okay, and yeah, this is an operation, one of the operation you can show. As you may know, over here why we introduce the MATLAB, and you can use the MATLAB in exam, because the computation is so complicated. You don't want to do the operation for more than 3 by 3 for the matrix. It's complicated. Okay, so let the MATLAB to do that. Okay, we see this kind of transformation, then you can do the calculation. So I would suggest you I don't want to do the homework for you, but you should practice. This exactly the exam question will show in the midterm. How can you solve? Find the homogeneous transformation related to each of the frames to the base x0, y0, z0. Find the homogeneous transformation for O1, O2 to the camera frame. And exactly we use the same skill and technique we introduced in the chapter 2. I believe I finished the important part for the chapter 2. Of course, it describes more detail because sometimes the textbook need to expand the pages. They can sell more money, but I should not say that. But they have a very fundamental introduction. I will say it's a good one for you to practice your English reading.